Hello, my name is Luís Gameiro. I'm here on behalf of the Telecommunications Institute of Aveiro, Portugal, and my co-authors Carlos Sena and Miguel Luís to present the article Context-Based Forwarding for Mobile ICNs towards the International Conference of Communications 2020. Nowadays, terms such as smart cities and Internet of Things are widely known, and they keep receiving attention and continuous evolution by the research community. And it is expected that in the near future, lots of devices such as mobile phones and sensors, and also vehicles, will be able to communicate seamlessly between each other. A factor which is very noticeable in the vehicular ad hoc networks, which are mainly comprised by vehicles and said devices. They present various characteristics such as the continuous node mobility and broad geographical dispersion that are noticeable by all the speed and mobility behaviors of the vehicles, all factors which contribute to a highly dynamic topology in the network. This, of course, doesn't come without any challenges, as high fragmentation can be noticed, and due to the intermittent connectivity, frequent disconnections are also noticeable. These factors contribute to a high latency on the ensuing communications that are performed in the network. On a separate context to that of the vehicle ad hoc networks, a new paradigm was created, the information-centric networks, that aimed at the reliable and efficient delivery of content by means of replacement of IP addresses for names, focusing directly on the content itself without the need to establish an end-to-end reliable connection. This makes them ideal for high latency environments such as the vehicular networks. Our work is focused on forwarding strategies for ICN networks being developed under the architecture named data networks, because we felt was more in line with the kind of work we wanted to develop and its distinct characteristics. Giving a brief overview, the NDN makes use of a hierarchical naming system, which allows for a more useful management of the packets. And they make use of two interest packets, the interest which are aimed at the finding and resolving of the content request, and the data packets which are aimed at the delivery of said content. They also make use of four different structures: the pending interest table, which focuses on the registering of the paths undertaken by the interest packets, the forwarding information base, which stores the known paths towards the content store, which mainly stores data, and the faces, which are the means of communication with the exterior by the nodes. Focusing more on the forwarding module, it works on a hop-by-hop basis in NDN, making use of meaning that each individual node will make its own assumption of the network conditions and use the previously mentioned structures and a forwarding strategy to try and get a vision of how the packet should be forwarded and to whom. While most works focus on the improving of this behavior, they do not make use of multipath capabilities as they usually perform using a best route approach. Also, while NDN makes use of hierarchical structured names in their packets, these are in no way considered in the decision undertaking or the forwarding workflow, which, despite their big impact in doing so. So our main focus is trying to improve upon these issues, resulting in the aforementioned context-based forwarding strategy, which mainly focuses on two key points: the context analysis, which aims at inferring content context and infer a proper baseline of which kind of link would be best suited to deliver the content request, and a neighborhood analysis to complement this by evaluating the neighborhood of a node and try to evaluate if it is possible to forward through such links or how to manage them. Both of these informations culminate in a forwarding strategy, which will ultimately decide on how to forward the packet. Focusing on the first one, it is divided into 4 aspects. The first one, we divided applications in a mobile environment into 6 broad domains based on their application in a smart city scenario. Their impact in the application layer, this is if they are impactful in case of packet losses, and also if they are prone or not to delays. We attributed 6 incremental values to each of these domains based on their importance. Secondly, the scope as to which a content belongs is not enough to understand its necessity to be successfully delivered, as a domain that in theory poses less importance to the network might contain data very important to the consumer which is requesting it. To this extent, we use the urgency meter defined in application layer that defines if the type of communication to be used should be adequate for its delivery or not. This ranges from non-urgent to extremely urgent. Then we divided the 4 types of links in a mobile environment in 4 baselines, and we split all the possible values resulting from a sum of the previous mentioned metrics into these 4 baselines, giving more emphasis to the least cost one, mainly because the multicast baseline of type of link may have a lot of impact on the network overhead. Then we use the urgency meter as an arbiter of repeated values across the 4 different established baselines. Lastly, in an effort to reduce the number of expired interests due to ineffective path selection, we introduced a metric called subpar neighbor links that mainly registers the number of interfaces through which a packet has traveled through, but which did not represent the highest count number of neighbors at the given time of the decision. This is, if this metric is at an average below an established threshold when a decision is being undertaken, the node in question selects the most neighbors link instead of following the normal forwarding workflow in an effort to make the request reach the content before expiring the entry. Okay, at this moment, we have a baseline of which kind of link would be best suited to deliver the content. However, this may not prove true if the neighborhood analysis presents conditions in the node that are not viable to do so. So a thorough investigation is performed to try to understand these conditions based on 3 heuristics: cost, the available bandwidth, and the number of types of neighbors. This is made on an interface basis of each node. Such information is then sent to the forwarding strategy for evaluation and ultimately decide on a specific interface to send the content, the request. Looking at the interest packets, this is the original NDN processing. We mainly implemented the changes at the time of visualizing the fee paths, meaning we identify which paths are available, and then we perform this analysis, and we select the best interface based on those instead of a best route approach. On the other side of the spectrum, when it comes to data packets, we kept the reverse pathing mechanic inherent to NDN, but due to the mobile environment, we introduced a new metric, the intop count, that basically takes into account the number of hops needed by the interest packet to reach the content, and if a node receives data which was not meant for him, but is in the same number of hops of the original consumer, meaning it should be in an area, it tries to make a last effort to make the content reach the user by sending data through all the remaining phases it has. Our changes were implemented in the well-known NDN simulator, which is an extension of the academic NES3 simulator, implementing the NDN logic. And the tests were realized under a touristic scenario, meaning that different areas of the city would have different content available. We used node behavior data retrieved from a real vehicular network in Porto City, Portugal, comprising of 4 hours of simulation and various nodes. We also considered 2 use cases, one with only urgent content requests and a mixed content requests. Looking at the use cases, what's important to notice here is all the mobile nodes only possess wireless capabilities for their communications with very limited cache sizes, while the producers have both wireless capabilities and cabled ones, connected to each other by 4 backend routers which only possess Ethernet. Both of these entities have strong cache sizes enough to store the data that travels through the network. We considered 2 variants, and one equal where all producers have all the available content, and a different one where the RSUs only have some of the content made available, and we'll need to use the infrastructure to reach certain content to send to the consumers. We also considered the caching replacement policies available in the simulator, which are LRU and priority FIFO in our experiments. Looking more at the consumers themselves, they will request content from all the mentioned domains, both urgent and non-urgent, and at a rate of 1 interest per second. So, going to results themselves. A higher number of interests which managed to reach a node in possession of the content was noticed across all the strategies. This can be noticed by the cache hits on the nodes, which ultimately results in increased content delivery across all nodes by means of rate of satisfied interests. This is our primary objective, which was achieved. However, this would be useless if the network overhead would also increase exponentially, meaning that it would have been unreliable to do so. However, this is not noticed as the number of sent interests remained constant across both strategies, while the number of received interests actually improved using our solution. This means that a higher number of interests successfully reached the content without unnecessary retransmissions being needed. On the other side of the spectrum, both sent and received data packets increased. This means that a higher number of interests successfully reached the content, which triggers more data transmission as we would expect. We can also understand better what happened over the course of the simulation by studying the network behavior. Mobility, of course, affects how interests are able to be delivered, and after the 2-hour mark, our solution was able to satisfy more interests than the native one, considering that we used the real data from a network environment, and which is unpredictable. So also the op count is affected by pathing and caching according to how which content is available at the nodes at a given time. And to that extent, after the 3-hour mark, context-based forwarding can deliver content with less ops than the native one, meaning that over the course of time, content was available earlier than in the native one. So as in a conclusion, our solution achieves higher interest satisfaction rates while maintaining transmission delays and network congestion at a stable rate. Also, neighborhood analysis is crucial for a better decision-making, aiding with mobility environments. Of course, there are always improvements to be made, and we aim to provide integration with the application layer to broaden the scope of the urgency metric. As we realize, we discarded security concerns, but we understand they are very important, and the clients can decide which urgency they want, which is not viable. Also, we bring mobility patterns to the context analysis process, since they make they allow us to make way more improvements on how forwarding should be undertaken, and evolution to a real network environment with real entities communicating between each other. So thank you. This is it. I hope I was clear enough, and have a good day.